Hello, and welcome to you all to the fourth webinar of the Process Bus Application series, with 5 webinars in total. In today's session, you will learn about distributed fault recording in a substation and how to parameterize the Cyprotec 7K85 fault recorder in Process Bus based on different customer scenarios. If this is the first webinar of the series that you're watching, I would like to encourage you to also watch the previous webinars on demand. The first one was about on how to configure transformer application with Process Bus. The second one was about on how to connect your line differential application using Process Bus in one line end and a conventional instrument transformers on the other one. The third one was about on how to create voltage selection and synchrocheck application based on Process Bus. My name is Luis Francisco, Sales and Business Development Manager at Siemens, and today I'll be moderating this live event. Please note that since you cannot ask questions directly to the presenter, we invite you to type them in during the presentation, whether in the question box or the chat box. Our expert will then address them after the presentations in a Q&A session. Now, for this webinar, we have the pleasure to have 2 of our main experts in these topics. The first one is Jose Malagon, and Jose will introduce you to the webinar and all the aspects required in the infrastructure of the Process Bus. Then come Marcus Graf, and Marcus will focus on the practical application of today, distributed fault recording based on Process Bus. And finally, they will show how to test such customers' workflows using Cyprotec Digital Twin. A couple of words about the first speaker, Jose Malagon. Jose started his journey at Siemens Colombia as design engineer. He was responsible to support the Cyprotec 5 release in the complete South America. He then moved to Siemens Australia as customer support team lead, and now is here in Germany, in our headquarters, as promoters for topics related to digital substation and power stability. Jose, my pleasure having you here. Welcome.
Hello, Luis. Thank you. Good morning and afternoon, everyone out there. It's a pleasure for me and my colleague Marcus Graf to have the opportunity to present you our Process Bus webinar series 2022. Today, we are going to talk in the first part about some supporting functions coming in Cyprotec 5 to test applications in digital stations. Then Marcus is going to explain how to apply Process Bus in the context of the distributed fault recording with some interesting applications that he will configure in Dixie, and then he will test also in Digital Twin. We wish you most success on watching this webinar. At first step, I would like to introduce the option coming with Cyprotec 5 to disconnect measuring current points. This option is quite useful when the feeder is handled by 2 circuit breakers and one of them goes to maintenance. And some tests are needed, or in case of some specific operation and switching states that are required in the station. Here in the slide, I have an application with transformer differential protection, where the high voltage side is having 2 measuring points for the side 1. In case that a test is needed, in one of the measuring points, it can be disconnected from the function group transformer side 1. And if a test needs to be done in the merging unit or in the circuit breaker, for example, primary injections, the disconnection of the measuring point avoids the ground operation of the differential protection. How to do that? It can be done via binary input of the relay, or it can be done via goose or a function key in the front of the device, also using 61E50 controllable mode. Other mechanism available in Cyprotec 5 is related with the possibility to stop sample values. It can be done for the complete device, as I am showing here in the slide. The merging unit 1 will stop publishing sample values to the work current relay that I'm having here, and to the fault recorder, 7K85. Or can be done per stream, where it's possible in a selective way, stop first the stream for the fault record, 7K85, and then stop the stream for the feeder protection 7SG85. There is a good thing that we need here, is to supervise the stream in the client side. The logical node LSBS can be used, which is created in automatic way once the link is made in the IEC 62150 system configurator. The stop SMB signal can be generated via a binary input or also using a CFC logic that is very comprehensive in CProtect 5. As you can stop the analog signals coming via sample values stream, it's also possible to stop the digital signals that are coming via GUS, also via 6150. In the example here in the slide, the GUS stop signal is generated to avoid that in case of testing of the overcurrent protection, the GUS signal is going to start the for record 7 key 85. Also, to supervise the GUS message, it is possible to enable GUS supervision in Dixie under the settings of the device. And then the logical node LGOS will be created to supervise them. CProtect Process Bus Client offers also the possibility to have the option to test. Support the test bit following the standard IEC 62150. The supported application modes are on, off, test, unblocked, or test blocked. When the device is in test mode, only signals with test flag will be processed. The device sends signals with a test flag set, and the binary outputs will be operated. The other option is, if the device is in test blocked mode, only signals with test flag will be processed, but the difference is that no binary outputs will be operated. Okay? The next option that we have with the test mode is that we can selectively use the test mode. What is the meaning of that? We can put the complete device in test mode, GUS and sample values, or individual function groups, that is also possible, as you see here in the screen, or individual protection functions, only GUS, or individual stage of the protection functions. And also, we can control the test mode via Dixie, via CFC, or via 6150 using the controller mode that we have in CProtect. As CProtect 5 supports the test bit, also the simulation bit is supported, not only for GUS, but also for SMBs, and it is implemented as described in the IEC 6150 standard. As an example, the device can be set to simulation mode using the IEC 6150 browser. In this mode, the device works with the original non-simulated signals, GUS SMB, for as long as it receives the same signals with the simulation bit that are generated from a test set. The signals without a set simulation bit are still processed from the original source. With that, this enables selectivity use of the simulation bit. The purpose of the simulation bit is to simulate GUS and SMB signals using test equipments. You can have any test equipment like Omicron, Megger, Double, whatever you have in your installation, and to test the subscriber devices without interfering with the operation of other devices using the same signals. The simulation signals and the real signals are present or can be present in the network at the same time. All right, that is so far for the infrastructure part of the webinar. Please use the chat to provide us your questions, and I will now hand over to Luis in order to introduce our colleague Marcus. Luis?
Thank you, Jose, and thank you for that introduction. I would like to just put into context the things that you said. I think that when you have a planned shutdown and you're about to do some inspection, maintenance activities, functional enhancements, or anything, it is possible to perform several tests via process bus systems. So whether it is stopping the sample value signals or stopping the GUS signals, also using the test mode, You can avoid unwanted malfunction of the protection scheme while leveraging on the technology to complete tasks in a fast and cost-effective manner. So, our next expert today is Marcus Graf. Marcus is one of our most experienced technical sales specialists, who now is promoting in the context of digital substation, the process bus technology, merging units based on CPROTEC 5 platform, and for recording portfolio. Marcus joined Siemens more than 30 years ago and was for many years in our R&D department for power quality software responsible. Marcus, welcome to this live event. Thank you for coming.
All right. Yeah, thank you, Luis. And also heartily welcome from my side to the audience. In the following 30 minutes, you will see how distributed fault recording customer scenarios looking like and how to configure it in Dixie 5. In the last section of the practical session, I will perform with you 3 test scenarios using digital twin. In customer scenario number 1, we want to use the 7key85 fault recorder internal trigger mechanism. Let us start on the left side of the slide. Here we can see 2 feeders, which will be measured, each one by a 6MU85 merging unit. That merging unit provides its sampled measured values, called SMP, in a 14.4 kHz stream on communication port F. The merging units are the so-called publishers. And on the right side of the slide is the 7key85 who subscribes that measured values on port F. In our example, the voltage trigger in 7key85 is switched on. The parameterization is 10% above the nominal voltage and 10% below the nominal voltage. When one of these limits are crossed, a fast-scan record will be initiated. The 2 merging units are connected to 2 function groups of type voltage current 3-phase. Each function group covers individual trigger parameterization. The yellow marked IEC61850 station bus on port J is connected to a CCAM PQS runtime server. That means as soon as a trigger criteria is fulfilled, the 7key85 starts a fault record, and when the fault record duration is over, the 7key85 sends an indication called RCD mate to the CCAM PQS, and the PQS transfers the fault record from the device memory into the CCAM PQS archive database. As soon as this transfer is finished, the new fault record will be listed in the View Incident Explorer in the HMI software CCAM PQ Analyzer. Exactly that procedure I will demonstrate in the digital twin session. Okay, the blue network number 4 is a so-called process bus, and the yellow one is a station bus network. Another standard use case is when a protection relay trips, then an internal fault record will be done for that single device. The benefit of the distributed fault recording with 7key85 is to cover several measuring points in one fault record. The right now shown customer scenario works as follows. The sampled measured values for the protection function inside the 7SJ85 are measured and provided via process bus by the merging unit 6MU85. In our case, on a 4 kHz stream. When the 7SJ85 measured current increases above 1.5 amps, it trips, and the definite time it's over, it will operate the circuit breaker. The trip signal will be sent via goose to the 7key85 and encourage the fault recorder to start a fast-scan record. Same procedure for the 7SJ85, which protects the feeder number 2 at the bottom. The experts in the audience will now say, hey Marcus, what are you showing right now can be realized much more compact, with 1 instead of 2 communication modules and a merging unit with an expansion module instead of 2 6MU85 merging units. You are absolutely right. However, for training purpose, I decided to set it up in that hardware constellation. Good so far. 7key85 will provide the fault records when its own trigger limits are overstepped and when the overcurrent relays are tripping. Let us now take a look into the essential points of configuration. On subscriber side, we have to define the merging unit as a merging unit and connect it to the IEEE 1588 PTP Precision Time Synchronization Protocol. The parameterization of the merging unit routing in the chapter merging unit, we can see the connection between measuring points and the streams. In our scenario, the measuring points are connected to two different streams. That's because we decided to different sampling frequencies in our process bus network. And in the properties window, we parameterize the streams in relation to sampling rate. In the screenshot marked in orange, the 14.4 kHz stream on port F for subscription in the Ford recorder. When you want to know more details about the merging unit parameterization, I recommend you to watch the first video of this Process Bus Webinar Series 2022. My colleague Jose Malagon explained in that video the merging unit parameterization step by step. Our next step is to define our 7key85 as a process bus client subscriber. And like we did already in the merging unit, the time synchronization is very important. Therefore, we will use IEEE 1588 Precision Time Protocol, PTP, also for the subscriber side. Instead of routing the physical voltage transformers and current transformers to the measuring points, we have to route a PP, process bus client, to the measuring points. The marked inconsistencies in the properties window reminds us that there are no sources assigned in the syscon, the system configurator so far. All right, let's go do that destination source assignments. Just to bring our customer scenario back in mind, we have two merging units, which represent the sources, and three destinations consisting of two 7SJ85 and one central Ford recorder 7KE85. Last but not least, there are three separate process bus networks. In that slide, we can see in the middle the sampled measured value mapping of the in orange marked 4 kHz network. The source on the left is a 6MU85 physically connected to current and voltage transformers on feeder number 2, and on the right side, the assigned destinations. Here, the overcurrent relay 7SJ85, which is responsible to protect feeder number 2. With reference to our overview slide, that green marked process bus connection is completed now. Similar to the slide before, here the source and destination connection between the 14.4 kHz stream of the merging unit, and on the right side, the 7key85 as destination. All right, we said that the 7key85 will be a process bus client, and the measuring point subscribes sampled measured values instead of physical voltage and current transformer connections. In the syscon, we defined a source as a 6MU85. Now, no more inconsistencies because the sources for our 7key85 are clearly assigned. But now we need to equip our Ford recorder to start recording. Therefore, we define two trigger functions for two kinds of characteristics. The first is a maximum and a minimum trigger level for the voltage. Either when the max limit of 480 kV is overstepped or the minimum level of 320 kV is understepped, the 7key85 starts to record a so-called fast scan Ford record. Equal parameterization for the current trigger. Thus, a measured current increases above 1.2 kiloamps or the current goes below 800 amps, a fast scan record will be started. That's so far from the internal trigger mechanism. However, we said that the 7key85 should start also recording when one of the overcurrent relays are tripping. For that, I've connected the trip indication of the 7SJ85 relays with the external start of the fast scan recorder in the 7key85. Keep in mind, the measurement input for that recorder is the 14.4 kHz stream published by the merging units. And do not forget to route that goose signals from booth relays into the ComTrade file to get to know afterwards what was the root cause for the recording activity. Okay, that have been a lot of theoretical information. However, my personal approach is that you understand what happened and why it happened when we test the scenarios in the digital twin after the parameterization in Dixie. Let me now show you how does everything looks like in the Dixie parameterization software. We switch to the Dixie UI. Here on the screen, you can see my Dixie application. First of all, let us take a look in the single line configuration. Double click. Here you are. In the single line configuration, we can see here the merging unit for the feeder number 1. And for example, feeder number 1, the 4 kilohertz stream is connected to the 7SJ85. This is for providing the measured values, the sampled measured values to the protection relay. And the 14.4 kilohertz stream of the merging unit is connected directly to the 7KE85 fault recorder. So the more detailed stream to the fault recorder and the 4 kilohertz stream between the merging units and the protection relay. Same procedure takes place for the feeder number 2. In the 7KE85, let us take a look on the communication settings, hardware and protocols. Let us select the communication port F. I open the properties window. And here we can see now the settings what are necessary. We have here the IP addresses. We have here the communication. This means the 7KE85 acts as a process bus client. Yeah? And for the network, we have also assigned the IEEE 1588 precision time protocol. In the settings chapter of the function group voltage current 3-phase number 1, we can see all the individual trigger settings. Just take a look in the voltage trigger. So voltage trigger for the RMS values comes up here. RMS voltage for number 1 is switched on, and everything above 480 kV primary and below 320 kV will initiate and trigger in the 7KE85. These are the so-called internal trigger mechanism. And now let us take a look in the protection relay, the 7SJ85 for the feeder number 1. Here in the settings chapter, voltage current 3-phase number 1, over current circuit breaker. Here is the settings about the trip and operate. Everything above 1.5 amps secondary will cause an trip and operate inside the protection relay. And in parallel, later on, we will see in the information routing matrix that this indication will be used to start the fast-scan recorder in the 7KE85. In the merging unit, just above the protection relay, and let me close here the other devices. In the merging unit, in the hardware and protocol, let us also here take a look inside the settings for the communication BD module. Here the settings are slightly different compared to the fault recorder. Also the IP addresses are assigned here. And in the communication, we can see now that the merging unit is selected as a merging unit. Yeah. Equal, like to the fault recorder, the time synchronization is IEEE 1588 precision time protocol. And when we now take a look in the measuring point routing of the merging unit, we can see that the merging unit is connected to the real voltage and current transformers on the rear side of the device. And in the measuring point routing, in the merging unit routing, we can see the two kind of streams. The communication module on port number F. When we select this one, we can see the properties window This is a 14.4 kilohertz, which will be connected to the 7key85 fault recorder. And in the communication port E, we have a second stream, which is providing the 4 kilohertz signal, which connects or provides the measured data to the 7SJ85 protection relay. Last but not least, in Dixie, let us take a look in the syscon. In the syscon, we have to care about goose and the SMV. In the sampled measured SMV, in the sampled measured value screen, let me open this one here. And when we select this data set, we can see it's connected via 14.4 kilohertz between the feeder number 2 of the merging unit, provides a measurement to the destination 7key85 fault recorder. When we close this one and open another one, the second one, when we select this data set, that we can see it's the 4 kilohertz connectivity between the feeder number 2 merging unit and the destination for the 4 kilohertz is the 7SJ85 protection relay. Okay, the goose chapter in the syscon shows us that when the feeder number 1 7SJ85 protection relay trips and operate, it provides an information via the goose network to the 7key85. Okay. The last step what we have to do in Dixie is to export on project level a so-called simulation file and import that simulation file into the digital twin to do the testing. Okay, now we come to the last session of the practical, the functional test. Let us switch back to the PowerPoint. So as we have now finalized the parameterization and have exported the simulation file from Dixie, I would like to show you the 3 test cases processed using digital twin. The 2 merging units, the 2 overcurrent relay, as well as the 7key85 are simulated in the digital twin. The first test case is to increase the voltage on the merging units until we overstep the maximum trigger level in the 7key85 and a fault record will be recorded. The second test case cares about the goose trigger. Means I will increase the current on the merging unit above 1.5 amps. That's the overcurrent protection function in the 7SJ85 becomes active and the relay trips. This trip indication will be sent via goose to the 7key85 and triggers the fast scan recorder. The last test case is related to communication supervision. Like my colleague Jose Malagón introduced you at the beginning of the webinar about supervision. I will block the goose communication on activating a binary input on the 7SJ85. That communication disturbance will be notified on the LED panel of the 7key85. All right, let us now switch to the digital twin. So now on the screen, we can see our CBRIC 5 digital twin. Let us take a look on the project page. Here we can see our devices, the fault recorder 7key85, the merging unit for the feeder 1, and the protection relay, the 7SJ85 on the feeder 1, and the same procedure for the feeder number 2. The devices are already started, and in the device view, we can see on the left-hand side where we can give some measured values for the simulation data. And on the right-hand side, we can see the list of the HMIs of our devices. The first test case is we want to activate, or so first I would like to explain you the front plate of the 7key85, what I've parameterized. Presetting of the 7key85 fault recorder is the LED number 1 and 2. This LED indicates when a fast scan record are started and when the fast scan record is finished. Means when the fast scan record is made. And this time difference between started and record made is individual parameterizable in the Dixie application. This means that's a recording duration. Fast scan start, fast scan record made, And the same procedure for the slow scan recorder is already predefined. Slow scan started and slow scan made. Today we have to concentrate on the fast scan because we are activating fast scan recorder for an internal voltage trigger, for a goose trigger. Additionally, what I've parameterized on the 7K85 is the 5051, the overcurrent trip indication for feeder number 1 and feeder number 2. This means when the current increases above 1.5 amps on the protection relay, they are tripping and operating and sending a goose message to the 7K85, and then this LED becomes red, and side by side with this LED, the fast scan will be started. Same for the feeder number 2. One more parameterization I've done here on the front plate is the Supervision constellation. I've added here on this position a so-called goose group alarm. It's right now off. That's okay, because all these goose communication are right now in a good manner. So feeder number 1 goose communication is okay, and the feeder number 2 goose communication is okay. When we are disturbing this goose, or when I'm doing a manual stop of this goose communication, you will see that this LED goes off and the goose alarm in generally becomes active. Good. Then let us do the first test case on triggering an internal, use the internal trigger of the 7K85 by over voltage. I'm selecting here the input on the left-hand side and increasing stepwise the voltage. And when it becomes high enough, then we can see now on the right-hand side that the fast scan record was started. And after the recording duration, it tells the fast scan record was made. Now the 7K85 is providing the so-called RCD made indication from the relay to the CCAM PQS. The CCAM PQS is hearing this or receiving this indication and is uploading the fault record from the memory of the device and stores it inside the archive of the CCAM PQS. And as soon as this transfer has taken place, we can see here now on the screen in the CCAM PQ analyzer, a new line appears. And this is exactly the record what we have just before created or simulated using the digital twin. It's a symbolic fault record. Here is a timestamp, German time right now, 10:30. And the trigger was a voltage trigger for RMS number 1. And the cause was that the voltage the max limit was overstepped. Let us take a look in this record. We are simply doing a double click on this. Then the SIGRA application starts up. And here in the SIGRA, we can see the sampled measured values, the 16 kilohertz signals of voltage and current. Here was an increase of the voltage. And interesting for us, at the bottom are the so-called binary signals. These binary signals I have also manually added to the in the information routing matrix to the record, to the fault recorder, to the fast scan. And now we can see here that the cause for it was the voltage trigger. It has started here and stopped here on the right side. The goose was okay, and there was no group alarm, and there was also no trigger from the feeders, from the overcurrent feeders, because here we can see no binary channels. Okay, then let us continue with the second test case. We go back to the digital twin, and now I'm switching from the fault recorder input to the protection relay. And here on the bottom, we have the current input for the simulation in the twin. I'm increasing this current also now stepwise up to 1.5. And when I'm going now one step more to the 1.6, this means we have seen just before that the current limit was 1.5 amps in the 7SG85. And increasing one more step, you will see that the feeder number 1 LED appears, and in the same moment, the fast scan start. So now 1.6, trip indication time takes place, and the fast scan will be done. This fault record, this fast scan record is now initiated by a so-called goose signal. And the same we can do for the feeder number 2. Here's the second SJ85. Let us increase the current also on this device. 4, 5, and in the next step, the feeder number 2 indication comes up, and then fastcade record will be done. Let us take a look in the analyzer. Okay, in the analyzer, the feeder number 1 trip fault record is already received. The cause in this case is a so-called flex start. This means it was a goose message. I do a double click now on this record. And when we take a look in the binary section on the bottom, we can see now that the trigger, the cause for this record was the overcurrent function 5051 of the feeder number 1. All right, close it. In between, the second also arrived here. The trigger cause for the second was the feeder number 2 tripped. I do a double click on that, scroll down, and now you can see the binary channel for 5051 over current feeder 2 are shown here in the comrade file. So, and the last test case I promised you is we want to test the supervision functionality. And for that, I have configured here in the digital twin these LEDs on the 7key85, and I have parameterized a binary input. I use this binary input 2.2 here to stop the goose communication on the protection relay. And after some observation time, it will be recognized now by the 7key85. This means the feeder number 1 goose OK disappears. It's not OK. And the global goose alarm becomes active. When we are removing this disturbance here, then everything comes back in a good shape. Okay. That's so far from our test cases. Let me now summarize it, all these points on the benefit slide. We need no dedicated voltage and current transformers for the fault recording. Therefore, no additional wiring. Because the 7key85 is, let me say, only one more subscriber in the existing process bus network. The pre-testing can be done using the digital twin, results in a shorter time to operation. The principles are 100% equal, like in the protection world. IEC 61850-9-2, Precision Time Protocol, PTP, boost redundancy concepts are supported. You can imagine that the 7key85 is a kind of central device, like the busbar protection. So now I'm now at the end of my presentation. I hope that you enjoyed it. Luis, I would like to hand over to you now.
Sure, Marcus. And thank you. Thank you for that great way to present actually live with the software on how to do the process bus applications and how you can help customers operating their automation system in different voltage levels, configurations and different market applications. Also, I think that it's good to see on how exactly it's done using the different engineering tools, whether it is Dixie5, you show the PQ analyzer, you show the Cyprotec digital twin, you show the SIGRA. So there's a bunch of softwares and tools available for you to make your life easier. And last but not least, I think that presenting also, the different test scenario using the Cyprotec digital twin is very powerful because you don't need to, put a full lab bench setup with actual devices, cables, test equipments, and it is really an eye-opener, I believe, on how convenient it could be to perform those tests, whether it is off-site or whether you are on-site but from a remote area. So now I would like to start with the Q&A session. As we said at the beginning, we will have a Q&A session, and I think we have actually enough time, plenty of time. I would like then to invite both Marcus and Jose to join us. Let me put actually questions. There's something that is coming very often, and I would like also to just tell the people, for those who are joining the first time, and if you are not having, let's say, or you didn't join on previous ones, you can do it step by step. Go to www.siemens.com and then you can go to product and services. Within product and services, you will find energy, and within energy, you will see energy automation and smart grids. As well, then you will go drop down, and you will see webinars for energy automation and distribution systems. You can all the time search then by keywords like process bus, series, and so on, and you will get there, and you will see all the recordings and all the material that have been uploaded for you in this series. That said, I would like to start then with questions, and there are actually many questions coming in. I like that. Let me see if I take one of the, I see here on the chats and question on the question box. So from the chat, what will be the maximum capacity for analog channels in the 7KE8 since it receives all through process bus? Who wants to answer that?
Yeah, the overall number of analog channels for 7K85 in conventional scenario is 40 channels. And with process bus, we have to reduce it by 8 inbuilt channels. This means the maximum is 32 channels for the 7K85.
Okay, perfect, Marcus. Another one is here regarding, I believe at the beginning, so this goes most probably to you, Jose. It is possible to stop only one SMB stream in CProtect 5 PB publisher, or it should be a fast task, or it should be a task of a PB client?
It's a task of the process bus server, the merging unit, and you can select what you want to stop. You can stop per stream. It's one option, or you can stop the complete sample values of the device. There are 2 options to do that. That means it's possible to stop per stream. It's now a new function that we have since 9.30 that you can stop the stream in a selective way.
Okay, perfect. Thank you. Hope this is the answer you're asking for. Another one here is, why do I need the 7K85? Because the protection relay also provides a complete fault record. That's a good one.
Yeah, good question. Thank you. Yeah. Why do we need 7K85 instead of the protection fault recorder? There have been a lot of reasons. Only a couple of them is, the first one, we have a high sampling frequency of 16 kilohertz compared to the 8, which we have in the protection only. We have a huge memory inbuilt in the 7K85. This means we can record and store longer fault records with a longer recording duration. The fast scan goes up to 90 seconds. The slow scan recorder is able to record up to 90 minutes, 1.5 hours, an extremely long time. But I think the most essential one benefit compared with the protection is you will get a fault record from your protection relay when the relay is tripping. This means the incident already happened. Yeah. With the 7K85, you can parameterize the trigger limits in a very, very sensitive level. This means the 7K85 provides you a fault record which represents some or records some anomalies in the network in a quite earlier state, just early before a protection relay is tripping. I think this is the most important point.
Perfect, Marcus. Thank you for that answer. And I see one good one here.
All a good one, isn't it?
Yeah, but I like this one. It says, can we link a remote fault recorder to the station using SAS, or substation automation system? For example, merging unit _ SAS _ fault recorder. Would it be possible? I told it's a good one. How to connect a remote fault recorder to your station process bus system?
But that is in my understanding, is the standard configuration that we have. Basically, you have the merging units, you have the fault record, and then you can integrate your fault record, for example, to SICAM PIS. SICAM PIS is having also all the power quality application and all the fault record application that we are having in PQS, as Marcus explained. And then you can integrate also your process bus station in the SICAM PIS, power automation system that we have. You can integrate the fault record application there. That is always coming.
And perhaps a good question, and this is only to get a little bit of more detail. What is the maximum distance that we can connect in a process bus, one device away from another? Is there a typical distance?
That is one topic related with our PD module.
Mm-hmm.
The PD module is having two SFPs.
Mm-hmm.
One is for 2 kilometers and another is for 24 kilometers.
Okay, up to 24 kilometers.
Up to 24. That means from the merging unit to the client.
To the client, exactly.
Mm-hmm. But normally we can say that a process bus architecture is installed close together. No?
Yes.
You have not such kind of long distance communication for process bus.
No, I'm just trying to give context to what the audience is asking, but thank you for the clarification. So 224. Let's go to another question. Let me see. And this actually, Marcus, I think that you mentioned that in the webinar, that there's a device constellation that can be somehow simplified. Can you elaborate on that?
Yeah,
because
sure.
they're asking how would it be possible to simplify what has been presented?
It's possible, yeah. As I said, I've decided to make it in a more granular way, to have 2 merging units, 2 protection relays, and 1 fault recorder on the right side. It can be simplified on using 1 merging unit base module plus an expansion module for the feeder number 2. Same procedure for the protection relay. Only 1 protection relay is necessary and receives the streams from the merging units. And also these 2 kind of streams, what we have parameterized, the 4 kilohertz and the 14.4 kilohertz, can be merged together or parameterized in 1 BD module. But as I said, I have decided to make it here in this way for a better understanding.
Okay, perfect. Thank you for the answer. I mean, I see many questions. I mean, it's mixed in the chat and the question box that relates to the testing, and more specifically on the different stop signals. Mm-hmm. Can you perhaps repeat in a very succinct way what are the different ways to test actually the system?
Okay. In conventional way, you have the test equipment, and you go to the station and you inject the currents to the device.
Yes.
That's one way. No? Now you have the merging unit, and you have the relay, the subscriber. Mm-hmm. Then you can go also with the test equipment to the merging unit, inject signals, and then you can use, for example, the test signal to put a whole device in test mode, for example. That is one way. You can test the complete device. You can test per functions. You can test per stage. It's a variety of things that you can do. In the test mode, you have block on test and not block, and then you can also avoid that the output contact close or not. Mm-hmm. That is more or less the same scenario that we have in the conventional way, where you have the test block.
Yes.
You are inserting the test block, and then you avoid the tripping to the primary equipment. In this case, we are doing that via software. That is one scenario. Mm-hmm. The other scenario is using simulation bit. In this case, you use a test equipment that is able to publish sample values in the network. Mm-hmm. You put this test equipment in the network, and this test equipment is going to have a simulation bit. But also you need to enable in the relay that this relay is going to be able to receive sample values with simulation bit. Okay. Then once that the device has the simulation bit enabled, then it's going to receive the sample values coming from the test equipment, and you can test your protection device using the sample values that we are simulating in the process bus network. This is another scenario that you can use.
Okay, perfect. Yeah, then I hope that to all of those who are asking regarding testing, that does a good summary of the first part actually of this webinar, which was about the infrastructure and how to do it. I see also many questions regarding VLANs. So how many good signals for recorder can subscribe to? This is one. And the other is, and VLAN, how many VLANs are possible or required for good communication from the merging units to the fault recorder?
Yeah, the answer is it depends, because we have to really take a look on the system on customer side. What is planned? What is the constellation? What kind of devices? what kind of different streams are necessary, and based on this statement, we can define how many VLANs we need. Yeah? At the end, we have to find a good balance in the communication network to don't overcrowd the 61850 process bus network.
There is one topic there that the customer is mentioned, or that the colleague that is in the chat is mentioned, is related if we have a VLAN for Goose.
Yeah, exactly.
That is something that I want to mention also, is that our application for process bus is able to transfer in the same communication application, in the same module, Goose and sample values. Okay. And we don't need an independent VLAN for the Goose and sample values. Okay, that's the first thing. We have different VLANs for applications, or no, we can have different VLANs. For example, one for boot bar protection, one just for the feeder, one, for example, for the forward recorder. That is one that we mentioned today. And also in our previous webinar, we saw also the voltage selection, and you can have another VLAN for the voltage selection application, or to stream the voltage from the boot bar. Then in this case, for example, we have 4 or 5 VLANs. That means, as Marcus said, it depends on the scenario that the customer is having in the station. Okay?
Perfect. Yeah, I think that the fact that question in particular is so open, right? There's many unknown to actually have a very precise answer on that one. But we have also very specific questions here, and I would like to use one of them to give an answer to those. So they said in the big substation we have 2 7K85 to cover all recording status and analog. Do you have any idea when we need bus differential operated signal to treat both 7K85 at the same time? Now we only have 2 choices. One is sending a Goose signal, and another one is send the bus differential operated signal to BI of both 7K85. So there's here a differential bus bar application, right? And they're saying, what are the different choices? Yeah, exactly, to trigger that for recording. Any comment on that one?
Yeah, once more, it depends. We have the possibility to trigger the forward recorder via binary signal. Yeah.
Yes.
And in this scenario here, what these colleagues in the audience are asking is when we need more channels in the 7K85 instead of the maximum 32 with the process bus. Then we need, a second forward recorder who cares about the remaining channels. And in the scenario, we have to trigger boost together. That's important. Yeah. This can be done via Goose or via binary channel. With Goose, I would like to recommend to use the sender timestamp in the 7K85 for the trigger line. In this case, the sender device, the publisher of the message, of the Goose message, provides its timestamp inside the Goose message. And this timestamp will be fetched by the 7K85, and this will be the trigger line. And this message will be sent to 2 Goose 7K85 together in parallel. And then we have a record, because all the equipment is PDP, IEEE 1588, high accuracy time synchronized, and very good forward record. And both are in sync.
Okay.
Yeah.
Any additional comment, Jose, or?
No, I was reading the question from the customer, from the colleague. I saw that he's already using Goose. He's already using the binary inputs. That is the right approach.
Okay.
Of course, the other option is to use the trigger by current, that the current is high, but we need to check if all the feeders are going to go up the current.
You mean the current inside the 7K85?
The 7K85.
Okay. In this case, one of the 2 7K85 is triggering internally, like I showed with the voltage.
Yes.
Therefore, we have to care that the second partner runs in parallel, starts in parallel the recording. No? This means, therefore, we will use also this internal trigger of the device number 1 to provide this message to the device number 2 to encourage the second device, let's record. Yeah.
Perfect. Yeah. Okay, thank you for the answer. Actually, very elaborated. Thank you, Marcus and Jose. One of the last questions that came in the chat is, how many fast scan and low scans are available in one forward recorder? They said, Also, why it is not integrated in the 7KE as additional module.
Okay, inside the 7K85, we call it a fault recorder, but this fault recorder has different kind of recording mechanism implemented. Yeah? The main one is a fast scan recorder, which records the sampled measured values of 16 kilohertz. This means 1, 2, 4, 8, or 16 kilohertz with a maximum recording duration of 90 seconds. Yeah? The second one is a slow scan recorder with a low sampling rate, however, and very long recording duration. Yeah? And these mechanisms are already inside the 7K85. And compared now, once again, the 7K85 with a protection relay, the 7K85 has a memory of 16 gigabyte on board, the SD card. And this SD card stores a lot of fault records. The amount of fault records can be seen in Dixie during parameterization, because this amount of records depends on, number one, the sampling frequency, number two, the recording duration, and number three, on the amount of channels. These three parameters have directly effect of the size of the fault record, in this case, of the amount of the record which can be stored inside the 7K85.
Perfect.
That's all.
Yeah, actually, that's quite descriptive. We have 4 minutes more, so I'm going to take a last question. And this last question is more about, let's say, what triggers fault recording, right? So there's a question: what is the cause of frequent tripping of the primary device? I mean, primary distribution substation. I mean, based on your knowledge, I mean, what typically triggers a fault recorder?
Normally, or mostly, the fault recorder will be triggered on the internal trigger mechanism. This means the customer want to monitor, they want to observe their energy network and check, as I said, just before a relay is tripping, do we have here some anomalies inside the network? This means they will parameterize the trigger limits for upper limit of voltage, lower limit of voltage, very, very sensitive. Yeah, to get in a very early state some variations in the voltage. Or another customer is interested on the rate of change of the current with the 7K85. This means the gradient trigger, delta T to delta magnitude, when the current increases more than 80 kiloamperes rise without overstepping the upper limit. They want to know this, and they want to know in fault record when this scenario happened. Yeah, okay. These are the most used trigger criteria. And sure, also some customers are connecting the protection relay when they are tripping just before operate, for example, send a goose message to the fault recorder, and fault recorder has to provide a detailed report, and detailed fault record with 16 kilohertz.
Okay.
Yeah.
Perfect, Marcus. I mean, I would like to call it now, and I would like to thank you all for the questions. So thank you also for you, Marcus and Jose, for being here and providing those answers. For the questions that were not answered live, you will receive those answers afterwards in that email that you used to register. Remember that you will have access to this recording, also to the other ones of the RIP series on demand. So we appreciate you watching it and also giving us feedback. So to all of you, this is what we have today in the fourth session from our Process Bus application series about distributed fault recording in a substation based on Process Bus. In our next and last session from this series, unfortunately, because I really like it, our expert will talk about solutions for cap banks based on Process Bus. Thank you for having us, and see you later.
Thank you. Bye.
Bye-bye.
Bye.
Ciao.